Oracle machines, theoretical black boxes in computation. Introduction. Imagine you're faced with a fiendishly hard puzzle, say, a massive Sudoku or a complex riddle, and beside you sits a magical black box. You simply feed the puzzle into the box, and instantly it lights up with the solution. Sounds like a dream, right? In computer science theory, we call this dream an oracle. An oracle machine is essentially an abstract computing machine equipped with such a black box oracle that can solve a specific problem in a single step. This idea might sound like cheating, handing off the hard part to a magical helper, but it's a powerful theoretical tool. By imagining what we could do if certain problems were easy, thanks to the oracle, we gain deep insights into computation itself. Today, we'll explore oracle machines in a way that even someone listening in the back row can grasp, much as the great Richard Feynman might explain, with clarity, a pinch of humor, and vivid intuition. We'll see how Alan Turing conceived of oracles, how they help us map the landscape of decidable and undecidable problems, and how they illuminate the relationships between famous complexity classes like P and NP, all without diving into heavy formulas. By the end, you should appreciate why oracles are considered black boxes that let us peek at alternate worlds of computing, and yet why they don't magically solve everything. So, let's open up this black box and see what's inside. What is an oracle machine? At its core, an oracle machine is just like a standard Turing machine, the fundamental theoretical model of a computer, with one crucial addition: access to an oracle. A Turing machine, recall, is an idealized computing device with an infinite tape for memory and a head that reads and writes symbols on that tape according to a set of rules. It's a simple model, but as Alan Turing showed, it can simulate any algorithmic computation. Now, imagine upgrading this machine with a special phone line to an all-knowing friend. Whenever our machine encounters a subproblem it can't crack, it calls up the friend, the oracle, and instantly gets an answer, as if by magic. Formally, we picture the oracle as a black box attached to the machine, which can solve some chosen decision problem in a single operation. The problem this oracle can solve, let's call it Oracle Problem O, can belong to any complexity class. It could be something we believe is hard, like an NP-complete problem, or even something outright undecidable like the halting problem. Whatever it is, the oracle has the power to decide it immediately. In short, an oracle machine is a Turing machine equipped with a magic subroutine for a specific language or problem, which it can use as often as needed, each use counting as just one step of computation. You might be thinking, hold on, this sounds like a sci-fi cheat code. Is this allowed? The key is, we're working in the realm of theory and thought experiments. We're not claiming we can build such a device. In fact, Turing emphatically said the oracle cannot be a machine, in any ordinary sense. Instead, we suppose it exists to explore consequences. By seeing what a computer could do with a hypothetical oracle, we learn about the inherent difficulty of problems and relationships between them. An oracle machine doesn't explain how to solve the oracle's problem, it just assumes the solution can be obtained mysteriously. This black box approach lets us separate the difficulty of the oracle's task from everything else. It's a bit like a thought experiment. If I had a genie that answers one class of yes/no questions instantly, how would that change what's solvable, or how fast it's solvable? Before diving deeper, let's clarify with a more down-to-earth analogy. Think of a difficult game, say a very complex maze. A normal computer, or person, has to navigate the maze step by step, which could take ages. An oracle for the maze problem, however, is like a magic map that instantly highlights the correct path to the exit. If you have that, you can solve the maze in one step. Now, having that ability, you might tackle an even bigger challenge that contains many mazes, solving each sub-maze immediately using the oracle. The oracle doesn't tell you how it finds the exit, it just gives you the answer. In complexity theory, we use oracles exactly in this way, as gadgets to instantly solve subproblems so we can focus on what remains. This helps us categorize problems into complexity classes relative to each other, and it reveals which problems remain hard even with certain powerful helpers. Turing's oracle, origins of the concept. The concept of an oracle machine goes back to Alan Turing himself. In 1938, as part of his PhD work, Turing introduced oracles while studying problems that a basic Turing machine couldn't compute. He was wrestling with the boundaries of computability, specifically, problems like the halting problem that he had shown to be undecidable. No Turing machine can solve them for all inputs. To probe deeper, Turing imagined a super powerful helper that could solve such a problem. He wrote, "Let us suppose we are supplied with some unspecified means of solving number-theoretic problems, a kind of oracle as it were. We shall not go any further into the nature of the oracle apart from saying it cannot be a machine." This quote is vintage Turing. He's basically saying, I don't care how this oracle works, just assume it can do what no ordinary machine can. Turing's aim wasn't to build a magical computer, it was to show relative limits. Even if you smash one barrier by adding an oracle, a new barrier appears beyond it. A little historical anecdote. The word oracle conjures images of ancient Greek prophecy, a source of infallible answers. Turing might have been inspired by a science fiction play he knew, Bernard Shaw's Back to Methuselah, which featured an oracle as a font of superhuman wisdom in the far future. Whether or not that's true, the name is fitting. The oracle in Turing's sense is like a mysterious sage that our machine can consult for truth on a specific question. Crucially, Turing's oracle was introduced to formalize the idea of non-computable problems. By assuming a solution source for an otherwise unsolvable problem, he could rigorously explore what lies beyond computability. One of Turing's fundamental insights was that no matter what single problem your oracle can solve, there will always be another problem that remains unsolvable even for a machine equipped with that oracle. In other words, there is no single, ultimate, oracle that answers all questions. There's an infinite hierarchy of ever harder problems. Turing used this to argue that there's no absolute hardest problem. For any oracle you add, you can formulate a new halting type problem that even that augmented machine cannot solve. This was a profound realization. It means the landscape of unsolvable problems goes on forever, climbing upward in what logicians later called the arithmetical hierarchy. To summarize Turing's motivation, the oracle was a theoretical device to chart the uncomputable. It wasn't about actually getting solutions from a mystical source. It was about understanding limits. Turing essentially said, imagine we had a magic box for this unsolvable task, what then? We get a new task that's unsolvable even with the box. The oracle concept thus highlights the relative nature of computability. What's unsolvable can become solvable if given a stronger machine, a machine plus an oracle, but that stronger model in turn faces its own unsolvable questions. In more modern terms, we call this relative computability, or Turing reducibility. Problem A is solvable relative to problem B if a machine with an oracle for B can solve A. This idea has become a standard tool in mathematical logic and computer science. So, Alan Turing, ever the visionary, not only gave us the universal machine, but also the notion of an oracle machine to explore the beyond. How an oracle machine works. Let's lift the hood and see how an oracle machine operates. Mechanically, we can envision it as a normal Turing machine augmented with an extra tape, or some similar device, dedicated to communicating with the oracle. This oracle tape is where the machine can write a question, an instance of the oracle's problem, and later read back the answer. The machine's set of states includes a special state, often called the query state, which triggers the oracle query. Here's essentially what happens when an oracle machine uses its oracle. 1. Preparing the question. The machine enters the query phase by writing the instance of the problem it wants the oracle to solve onto the oracle tape. For example, writing down a particular input for which it needs to know yes or no. 2. Querying the oracle. The machine then transitions into the query state. At that moment, in a single computational step, the oracle is invoked. Think of it as the machine freezing and the black box taking over instantly. The oracle reads the question on the oracle tape and magically produces the correct answer. 3. Receiving the answer, the oracle writes the answer, often just a single bit, yes if the input is in the oracle's language, or no if not, onto the oracle tape. The machine state then changes to a special response state indicating the answer, say, Q_yes or Q_no, and the machine resumes its normal operation, now aware of the oracle's solution. This entire sequence, write question, ask oracle, get answer, counts as only one step in the machine's computation. That's the crucial part. No matter how complex the oracle's problem is, from the perspective of the machine's running time, it's just one step, as effortless as a single addition in a basic computer. After that, the machine continues its own processing with the benefit of the oracle's information. It can loop, make further computations, even ask the oracle more questions if needed, each query, again, being one step each. Illustration of an oracle Turing machine with a separate oracle tape. The oracle, the black box, on the right, can answer queries written on the oracle tape in a single step, returning a yes/no answer that the Turing machine uses in its computation. In essence, an oracle machine's computation looks just like any other Turing machine's computation, except whenever it bumps into a subproblem that is of type O, the oracle's specialty, it can jump over that hurdle by querying the oracle. This is analogous to a subroutine call in programming, with the difference that the subroutine here is magically powerful and runs in one step regardless of input size or difficulty. Because of this property, we often say an oracle machine relativizes computation to the oracle's language. It's like saying, relative to the assumption that problem O is trivial, solvable in unit time, here's what else we can solve efficiently. To make this even more concrete, let's walk through a tiny example. Suppose we have an oracle for a simple math problem, say, determining whether a number is prime, just an example of a decision problem. An oracle Turing machine with this prime testing oracle could solve tasks like, given a big number, does some related number meet a certain property? By delegating the prime checks to the oracle. The machine would write numbers on the oracle tape, enter the query state, and bing! The oracle writes back, yes, if the number is prime, or no, if not, in one step. The machine then uses that answer to proceed with the rest of its algorithm. If it needed to test many numbers for primality as part of a larger computation, each test would be instantaneous by virtue of the oracle. The same machine, without the oracle, might have had to grind through a long division or a probabilistic algorithm for each test, taking potentially many steps for each. With the oracle, those tests don't cost time. That's a huge advantage, and exactly why we want to analyze it. By giving our theoretical machines such unfair advantages, we learn which problems would become easy if a certain hard problem were easy. This is fundamentally how complexity theorists use oracles. Before moving on, it's important to note that an oracle is problem-specific. Each oracle can only answer one kind of question. If you have an oracle for, say, the halting problem, that's amazingly powerful for certain tasks but completely useless for, say, telling prime numbers apart, unless you encoded that as a halting problem somehow. Similarly, an oracle for SAT, the Boolean satisfiability problem, can solve SAT instances instantly, but it won't directly tell you if a number is prime. In other words, an oracle is like a specialist, a genius savant in its domain, but it doesn't automatically solve everything. We often name the oracle after the problem it solves, e.g., Oracle A might solve language A. So we talk about a Turing machine with Oracle A. Finally, let's dispel a potential confusion. Is there anything logically fishy about assuming a machine that can solve an undecidable problem, like the halting problem? It might feel like a paradox. If it can solve halting, could it solve its own halting problem and cause a contradiction? The resolution is that the Oracle machine is a different model of computation. It's more powerful than a standard machine, but still not all-powerful. For example, a machine with a halting problem oracle can indeed decide whether ordinary Turing machines halt. However, as Turing pointed out, that machine cannot necessarily decide whether a machine of its own kind, i.e. another oracle machine with the same oracle, will halt. There's still a limitation. In fact, the statement, "No machine can compute such an oracle for halting," still holds. It just means no ordinary machine can. We've simply defined a new, stronger machine model when we introduce an oracle. And that new model has its own halting problem it can't solve. So no contradictions arise. Instead, we get a hierarchy. Basic Turing machines lesser than oracle machines with one oracle lesser than oracle machines with an even stronger oracle, and so on ad infinitum. This hierarchy, which we'll touch on next, is a cornerstone of computability theory, illustrating that with greater power comes greater unsolvables. In summary, an oracle machine works through a simple query response mechanism with a black box helper, and this theoretical setup, while imaginary, is internally consistent and extraordinarily insightful. Oracles in computability theory, the halting problem and beyond. To truly appreciate oracle machines, let's delve into a classic example in computability theory, using an oracle for the halting problem. The halting problem is the granddaddy of undecidable problems. It asks, given a description of a program and its input, will that program eventually halt, stop running, or will it run forever? Turing famously proved in 1936 that no ordinary Turing machine can solve this problem for all possible program input pairs. It's impossible to write a universal algorithm that infallibly predicts halting for every other algorithm. This was a groundbreaking limitation result. Now imagine we do something audacious, introduce an oracle for the halting problem. That is, we assume there's a black box, call it OHalt, which when given the description of any program and input will immediately tell us halts, or does not halt, correctly every time. With such an oracle in hand, previously unsolvable questions become trivial, at least relative to this new machine. A Turing machine with the OHalt oracle can, by definition, decide the halting problem in one step. It just asks the oracle. That's pretty mind-boggling. We have effectively decided an undecidable problem, but only because we augmented our machine with a superhuman ability. The resulting machine is often called a halting oracle machine or sometimes a Turing jump machine, because we've taken a jump in power by one level. What can such a machine do? For starters, it could solve some problems that were impossible before. For example, there are many problems in computability theory known to be equivalent to the halting problem, like certain logical decision problems. Our oracle machine can solve all those easily. However, and here's the twist, does this mean our oracle machine is now omnipotent, able to solve every decision problem imaginable? No. It still cannot solve the next level of problems, such as the halting problem of machines that themselves have a halting oracle. That is a more powerful problem. Concretely, consider the task. Given the description of an oracle machine that has a halting problem oracle, will that machine halt on a blank input? This is a new halting-like problem, one level up. And it turns out that even our original OHalt-equipped machine cannot answer that question in general. We would need an even stronger oracle, a halting oracle, so to speak, to solve that. And if we had that, there'd be yet another halting problem for the double oracle machine, and so on. In other words, by giving a machine a halting oracle, we've ascended to a higher rung on the ladder of unsolvability, but the ladder keeps going infinitely upward. This infinite ladder is formalized as the arithmetical hierarchy, and related hierarchies in logic. At level 0, we have regular decidable problems. At level 1, we have the halting problem, often denoted 0 foot in Turing degrees, and all problems reducible to it. At level 2, we have the halting problem relative to a halting oracle, 0 foot, and so forth. Each step up corresponds to an oracle for the previous level's unsolvable problems. Turing proved that for any oracle you assume, say an oracle that solves some set A of undecidable problems, there will always be another problem, the halting problem relative to a, that lies beyond the reach of that oracle. This property is sometimes called Turing incompleteness. No oracle, short of a mythical all-powerful one, makes the world of computation closed under. There's nothing harder. There's always something harder. So oracle machines in computability give us a structured way to talk about relative decidability. We say, problem X is decidable relative to problem Y. If a machine with an oracle for Y can solve X. This is exactly the idea of a Turing reduction. X is Turing reducible to Y. If y itself is not decidable normally, this statement doesn't mean x is absolutely decidable. It just means if y were easy, x would be easy. For example, any problem x in the halting problem level, often called RE-complete problems, is unsolvable in isolation, but it is solvable relative to the halting oracle. By using oracles, we can classify problems by their degree of unsolvability. Two problems that are interreducible via oracles belong to the same Turing degree. They're equally hard in a maximal sense. The halting problem represents one such degree, often called the degree of unsolvability 0 foot. Problems in higher degrees need stronger and stronger oracles to solve. Let's put this in a Feynman-esque narrative. Suppose you're an explorer of problem space, climbing an endless mountain. The base of the mountain is the land of decidable problems, things every ordinary computer can do. You encounter a sheer cliff, the halting problem. No amount of ordinary climbing gets you past that. It's unscalable by a normal computer. So you imagine, what if I had a helicopter, an oracle, to lift me past this cliff? Boom, with the helicopter, you land on a higher ledge. Now you see further peaks, even harder problems ahead. You've defeated the halting problem, but on the horizon is another cliff, the halting problem for machines with helicopters. Your helicopter can't get you up that next one. You need an even more powerful flying machine. And even if you get that, another cliff awaits in the distance. The landscape is infinite, and each oracle is like acquiring a new tool that gets you to the next plateau, only to reveal a new challenge. There is no top of the mountain. This vivid picture is precisely what Turing's oracle concept formalized. It's a humbling view of computation. No matter how many problems you can solve, there's always a harder one if you allow yourself to dream up a strong enough machine. Instead of despairing, computer scientists took this in stride. They mapped out these degrees, and now we understand a great deal about the structure of unsolvable problems thanks to oracles. To recap this section, in computability theory, oracle machines let us talk about solving the unsolvable if given help. A machine with a halting oracle can solve the original halting problem, and ones like it, instantly, but faces a new halting problem of its own. This gives rise to an infinite hierarchy of increasingly powerful oracles and correspondingly harder problems. It shows that unsolvable isn't a single yes/no concept. There are shades and grades of unsolvability. And importantly, it's not self-contradictory to assume a machine can do something a normal machine can't. It just means you've stepped into a richer theoretical universe. Oracles are our ticket to systematically exploring those universes. Oracles in complexity theory. Relativized complexity classes. Switching gears, let's talk about complexity theory, where the focus is not just on what can be computed at all, but how efficiently it can be computed. In complexity theory, oracles help us compare the power of different complexity classes, like P and NP, by essentially asking, what if we give one class a head start by solving certain subproblems for free? This is analogous to how we used an oracle to explore decidability, but now the question is about time or resources. First, a quick refresher. Explain Feynman-style P is the class of decision problems that are solvable in polynomial time by a deterministic algorithm. Informally, problems that are, efficiently, solvable by a normal computer. Think of things like sorting numbers, finding the shortest path in a graph, etc. NP is the class of problems for which a given solution can be verified in polynomial time, or equivalently, by the magic of nondeterminism, problems that a guess-and-check machine can solve in polynomial time. The quintessential NP problems are things like the satisfiability of logical formulas, SAT, the famous traveling salesman problem, find a route visiting cities with limited distance, and so on. These are problems that we don't know how to solve quickly, but if someone hands us a candidate solution, like, here's a route of length lesser or equal than k, or here's an assignment of variables that makes the formula true, we can check that solution quickly. The big open question in complexity theory is, of course, P versus NP. Are these classes actually different? Or could every NP problem be solved as fast as P problems? Most of us believe NP problems are inherently harder than P problems, so P is not equal to NP. but we have not been able to prove it. Enter oracles. They can't solve the P versus NP question for us, but they can show us something profound about the nature of any potential proof. How? By creating hypothetical worlds where we know the answer one way or the other. Consider an oracle for an NP-complete problem. NP-complete problems are essentially the hardest problems in NP. If you can solve one of them efficiently, you can solve all NP problems efficiently via polynomial time reductions. A classic NP-complete problem is SAT, Boolean satisfiability. Now imagine a world where we have an oracle for SAT. That means our machine can ask, "Is this Boolean formula satisfiable?" and get an answer in one step, regardless of how large or complex the formula is. Let's denote this oracle as OSAT. What's the power of a polynomial time machine with this oracle? We call the class of problems it can solve P to the SAT, read P with SAT oracle. But since SAT is representative of NP's difficulty, P to the SAT actually equals P to the NP, P with an oracle for any NP problem. In other words, giving an efficient machine the ability to instantly solve SAT is as good as giving it a genie for all NP tasks, because any NP problem can be turned into a SAT question by a polynomial time reduction, and our P machine can certainly perform that reduction and then ask the oracle. So P to the NP is the class of problems solvable in polynomial time if you have a subroutine that answers NP problems instantly. You can think of P to the NP as one level up from P in terms of power. It's at least as big as NP, clearly, because with the oracle we can solve NP problems by definition, and potentially strictly bigger. What kinds of problems lie in P to the NP? For a simple example, consider a problem like, given two different NP puzzles, is at least one of them solvable? A normal NP machine can't easily do that, because it would have to solve both potentially. But a P machine with an NP oracle could just ask the oracle for puzzle 1, ask for puzzle 2, each in one step, and then answer accordingly. More dramatically, P to the NP includes the so-called NP with multiple queries problems. For instance, does there exist an X such that for all Y, some condition C of X and Y holds? This is a second-level logical statement, often associated with the class sigma 2 to the P in the polynomial hierarchy. A P machine with an NP oracle could solve a sigma 2 problem by cleverly using the oracle twice, once to existentially guess X, once universally over Y. In fact, P to the NP is equal to that class sigma 2 to the P. And if you allow more queries in a hierarchical fashion, you climb up the polynomial hierarchy P with an NP oracle, with another NP oracle, and so on, yields levels sigma 2 to the P, sigma 3 to the P, etc. We suspect this hierarchy doesn't collapse, i.e., each level is more powerful than the last, but that's another unproven conjecture akin to P is not equal to NP. Now, here's a fascinating thing oracle machines allowed complexity theorists to discover in the 1970s. It's possible to have different oracles that make P versus NP turn out differently. In a landmark result, Baker, Gill, and Solovay, 1975, constructed two hypothetical oracles, call them A and B, with opposite properties. With oracle A, it turned out that P to the A equals NP to the A. In that imaginary world, P equals NP. Any problem in NP could be solved in polynomial time when you have oracle A's help. But with oracle B, they showed P to the B is not equal to NP to the B. In that world, even with oracle B, giving machines extra power, NP problems still stayed harder than P problems. What does this mean? It means the question, P versus NP, is relativization dependent. If you proved a statement about P and NP that remained true even if all machines had access to an arbitrary oracle, we call such a proof relativizing, you'd be in trouble, because we know there's some oracle world where P equals NP and some other where P is not equal to NP. Therefore, no relativizing proof can resolve P versus NP in our real world. In plainer language, any proof technique that doesn't somehow break the model of computation in a non-relativizing way will fail to separate P from NP, because if it worked, it would also work in those oracle-altered worlds, which is impossible. This was a huge insight. It told researchers that many standard methods, diagonalization, simulation arguments, etc. Likely won't resolve P versus NP, because those methods typically hold even with oracles, they relativize. Indeed, decades of work have confirmed that most techniques we have are relativizing, and thus not sufficient for P versus NP. This relativization barrier, discovered via oracle machines, has guided complexity theory ever since. It's as if oracles gave us alternate universes to test any prospective proof. If your proof would also imply something in every alternate universe, every oracle world, but we know some alternate universe where the conclusion is false, then your proof cannot exist. It's a very meta-theoretical use of oracles, using them not to solve problems, but to constrain the kind of arguments we consider viable. Let's ground this in a more intuitive scenario. Pretend P versus NP was a question about two characters, Polly, for P, and Nandi for NP, and whether they are actually the same person in disguise or genuinely different. An oracle is like a mask or context that can change how they appear. Baker, Gill, and Solovey basically said, I can design one mask that makes Polly and Nandi look identical, and another mask that makes them look as different as night and day. If your method of telling them apart works no matter what mask I put on them, i.e. it relativizes, then you're out of luck because I have a mask under which they look identical. Your method would falsely conclude they're the same in that case. Therefore, any successful method must peer beneath the masks in a way that standard methods don't. In real complexity terms, any proof that P is not equal to NP will have to use non-relativizing techniques, perhaps algebraic, analytic, or circuit-based methods that don't hold in arbitrary oracle worlds. Oracles have been used to explore many other relationships too. For instance, by considering oracles, researchers have shown results like, with a random oracle, imagine picking an oracle problem at random. It's true with probability 1 that P is not equal to NP in that oracle world. In fact, with a random oracle, a lot of separations happen. For example, one can show an oracle relative to which P is not equal to NP is not equal to co-NP and a whole hierarchy separates. This provides evidence that in our real world P is not equal to NP, because a random oracle, a kind of generic scenario, tends to make them different. However, this is not a proof, it's more like a heuristic hint. As a counterpoint, there are also oracles relative to which other surprising things happen. For example, there's an oracle relative to which NP equals P space, another complexity class. The take-home message is, complexity theory has benefited enormously from the oracle concept to map out the if this were easy, then that would follow relationships among classes. By studying relativized complexity classes like P to the A, NP to the A, co-NP to the A, P space to the A, etc., we've developed structures like the polynomial hierarchy, layers of NP oracles, and identified barriers to certain proofs. Let's put some structure to those insights by listing a few ways oracles show up in complexity theory. Relativized classes. We define classes like A to the B to mean class A with an oracle for problem B. For example, P to the NP is P with an NP oracle, which we often think of as the second level of polynomial hierarchy. By comparing P to the A and NP to the A for various oracles A, we investigate the P versus NP question indirectly. Proof limitations, relativization barrier the existence of oracles like A and B, from Baker-Gill-Solovey, with P to the A equals NP to the A and P to the B is not equal to NP to the B shows that any proof of P is not equal to NP must be non-relativizing. Similar oracle-based arguments suggest barriers in other problems, like separating other complexity classes or proving circuit lower bounds. Hierarchy collapses or separations. If for some oracle A we found P to the A equals NP to the A equals something else, that might hint at a possibility or impossibility in the unrelativized world. For example, if someone attempted a technique to prove NP different from co-NP, we know that technique must not hold relative to all oracles, because there are oracles where NP to the A equals co-NP to the A even if we suspect NP is not equal to co-NP normally. Oracle constructions as games. Often, constructing an oracle separation is like a cat and mouse game of diagonalization. We carefully define a problem A that one class can solve but another can't when they have access to A. This is very useful pedagogically for understanding why a direct diagonal argument fails to separate P from NP, because the adversary can always foil you by encoding answers in the oracle. It's a bit technical, but it's something you learn in an advanced complexity course, and it builds intuition about the limits of algorithms. Overall, oracles in complexity theory give us a laboratory to test hypotheses about what additional power allows. Just as in computability theory, oracles built an infinite computability hierarchy, in complexity theory they help outline the polynomial hierarchy and other refined class separations. Oracles can also be used to define complexity classes. For example, the class IP, interactive proofs, turned out to equal P space, but it was first understood by considering oracles and randomness. They even creep into cryptography, which we'll touch on next. The important thing is, an oracle is not a physical thing we have, but a conceptual tool that says, suppose we could do X instantly, how would that affect Y? In that sense, it's like a supercharged what if scenario analysis for algorithms. It helps us understand relative power without actually solving the hard problems themselves. Other applications and related topics. Oracle machines don't just live in the realm of pure theory for P versus NP. They also appear in other contexts and inspire related concepts. Let's briefly explore a few. Oracles and cryptography. In cryptography, it's common to treat certain functions as oracles to reason about security. For instance, the random oracle model assumes that a cryptographic hash function behaves like a completely random function that everyone can query, effectively a black box that gives random-looking answers to each input, but consistently the same answer for the same input. Protocols proven secure in the random oracle model are shown to be secure if the hash truly acts as a random oracle. This is a way to simplify proofs, by replacing a concrete function with an ideal oracle that's easier to analyze. It's a bit controversial in that random oracles don't exist in reality, but many practical protocols are designed and tested under this heuristic model. Additionally, terms like oracle pop up in cryptographic attacks. For example, an oracle attack is when an attacker can query some encryption or decryption device to gather information, like a padding oracle attack where an attacker exploits a device that reveals whether a ciphertext's padding is valid. All these uses carry the same spirit. An oracle is an entity that will output answers to certain queries upon request, which is exactly Turing's notion, though in cryptography the oracle might be an actual party or system you interact with. Black box analysis. The notion of an oracle aligns with the idea of black box subroutines in general. In software testing, for instance, a testing oracle is something that tells you whether the output of a program is correct for given inputs. This use of the word oracle is a bit more general, but it highlights the idea of a reliable external source of truth. In algorithm design, especially randomized algorithms and heuristics, we sometimes analyze performance with respect to an oracle comparator. For example, how well a compression algorithm does relative to one that magically knew the best compression. That's using an oracle as a benchmark. Interactive proofs and advisors. In complexity, there are concepts like interactive proof systems and Merlin-Arthur games where one party, Merlin, an all-powerful prover, can be seen as an oracle feeding answers to a polynomial time verifier, Arthur. This is not literally an oracle machine, but the idea is similar. Arthur is limited, like P. Merlin has unlimited computational power, like an oracle answering NP questions, or even beyond. Interestingly, results like IP equals P space showed that even a polynomial time verifier, interacting with a powerful prover, can solve problems as hard as P space, which is beyond NP. This again resonates with the oracle idea. Giving a limited machine access to a powerful helper increases its power. Here the helper provides proofs instead of just yes/no answers, but it's in the same family of ideas of relativized power. Turing reductions and relative computation. As mentioned earlier, oracle machines formalize the idea of Turing reductions. If problem X is reducible to problem Y, in the Turing sense, it means a machine that can solve Y, or an oracle for Y, can be used as a subroutine to solve X. This is a key concept in computability. to classify unsolvable problems by relative solvability, and in complexity, to define completeness. A problem is NP-complete if every NP problem is reducible to it, which means if you had an oracle for that NP-complete problem, you could solve all NP problems efficiently. So oracles are baked into the definitions of complete problems and hardness in complexity theory. When we say SAT is NP-complete, it implicitly means SAT can serve as an oracle representative for all NP problems. Exactly what we leveraged in the earlier section to say P to the SAT equals P to the NP. Relative models in other areas. Oracles have analogs in other computational models. In quantum computing, for example, we often discuss a quantum oracle, not in the sense of solving an uncomputable problem, but as a black box function that a quantum algorithm can query. Grover's algorithm, for searching unsorted databases, is described in terms of queries to an oracle function that marks the solution. Shor's algorithm uses an oracle for period finding. In these cases, oracle just means a subroutine given as a black box. Complexity theorists also talk about classes like BQP, quantum polynomial time, relative to an oracle, etc., to study quantum classical comparisons with an oracle's help. Another example, in learning theory, an oracle might be a teacher that can answer certain types of queries, like membership queries in Engluen's model of learning DFA. These are all variations on the theme of one entity that supplies answers that would otherwise take a lot of computation. To ensure we meet our promise of a thorough lecture, let's highlight the key takeaways in a concise form. Oracle machines, though abstract, have a few major roles in theory, exploring what-if scenarios. By assuming a hard problem is suddenly easy, solvable in one step, we can deduce how other problems relate to it in difficulty. This helps map out complexity classes and reduction relationships. Formalizing reductions, oracles provide a rigorous way to say X is at most as hard as Y. If X can be solved with an oracle for Y, using polynomial time outside of that, then X is Turing reducible to Y. This notion underpins NP completeness and the whole theory of hardness. Complexity class separation and hierarchies. Oracles give rise to relativized versions of classes, like P to the NP, and the polynomial hierarchy. They show how adding resources shifts power. By seeing patterns across levels, e.g., pH might collapse if certain inequalities hold, we form conjectures about the real world. Barriers to proof techniques. The existence of contradicting oracle worlds, P to the A equals NP to the A versus P to the B is not equal to NP to the B, indicates limitations of techniques, relativization, in resolving major open problems. This directs researchers toward new methods. Cryptographic reasoning. Treating hash functions or adversaries as oracles is common in security proofs, random oracle model. Oracles here model an idealized component, or an attacker's limited access to a system. It's a way to simplify and argue about the real world by comparison to an ideal scenario. Each of these could be a lecture in itself, but the common thread is the powerful intuition oracles give us. They isolate a source of difficulty, the oracle's problem, and let us ask, if that difficulty weren't there, what then? Answering that yields deeper understanding of the difficulty's impact. Conclusion. In wrapping up, let's step back and appreciate the journey. We began with a seemingly wild idea, a machine that can solve an arbitrarily hard problem in a single step, as if by consulting a mystical oracle. Far from being mere fantasy, this construct, the oracle machine, has proven to be an extraordinarily fruitful thought experiment in theoretical computer science. By imagining a world where a certain problem is easy, we shine light on the structure of problem relationships in our actual world. As Richard Feynman might have put it, it's like we playfully trick nature. In our minds, give ourselves a magical advantage, and see what breaks or what new vistas open up. We saw how Alan Turing introduced oracles to explore the uncomputable, revealing an endless hierarchy of harder and harder problems beyond the halting problem. This taught us that no matter how high you climb in computational power, there's always a higher peak, a humbling and profound insight. We then moved to complexity theory, where oracles allow us to relativize classic questions like P versus NP. Through oracle constructions, we learned that our current techniques can't resolve P versus NP because they'd have to work in make-believe oracle worlds where the answer can differ. Oracles also helped us define classes like P to the NP and the polynomial hierarchy, sharpening our understanding of, if I had this ability, I could do that, in terms of efficient computation. We even peeked at related areas, cryptographers using oracles as idealized models, and computer scientists using the term oracle for black box subroutines in various contexts. Throughout this discussion, a few themes have emerged. One is relativity in computation, the idea that what's easy or hard can change if you change the ground rules, like giving access to an oracle. Another is limitation. Oracles show that there are intrinsic limits to what certain approaches can achieve, since adding an oracle can sidestep those approaches. And a third is imagination. The oracle machine is a triumph of using imagination to understand reality. We don't have halting problem solvers in the real world, but thinking about them guides us in the real world of what computers can or can't do. It's important to remember that oracle machines are a theoretical construct. No one expects to find a halting problem oracle in a box at the store. When we use oracles, we're not claiming to have solved these problems. We're doing a kind of scientific Gedanken experiment, thought experiment. By considering an oracle as a given, we isolate the role of a problem's complexity in broader computations. It's akin to a physicist saying, assume no air resistance. To study a falling object's motion, we assume away a complication to see underlying structure, then we put the complication back and see what's changed. With oracles, we assume away the intractability or unsolvability of some problem to see how it affects the world of computation. In a real classroom, this is the point I, channeling Feynman's enthusiasm, would lean over the desk and say, so you see, the oracle isn't there to help us build supermachines. It's there to teach us about computation. By seeing what a hypothetical supermachine could do, we appreciate the value and difficulty of the problems we don't know how to solve. We also get a rigorous language for reductions. A is easier than B, since it can call B as a subroutine, and for complexity separation. The oracle concept ultimately reinforces why problems like P versus NP are so hard, because even imaginary magic boxes can't simplify them in a straightforward way. Let's end with a final colorful analogy. Think of each decision problem as a locked door. An oracle for that problem is like a master key for that one door. It pops it open instantly. Oracle machines are like adventurers equipped with certain master keys exploring a mansion of many locked doors. By giving an explorer a master key for door X, we can see how far they get and which other doors still block them. We learn that some doors, once opened, give access to entire wings of the mansion, like SAT unlocks all NP problems. Other doors lead to yet more locked doors deeper inside, like the halting problem opens a wing that contains a new unpickable lock further in. Through this process, we map the mansion's layout. We might not have the keys in real life, but we at least know what having them would imply. And that is immensely valuable knowledge. In conclusion, oracle machines serve as our theoretical black boxes that illuminate the structure of computation. They embody the idea that sometimes to understand a limitation, you push against it with an imagined freedom. In doing so, we've deepened our understanding of everything from logic puzzles to the most profound questions in computer science. So the next time you ponder, could there be a shortcut to solving this problem? Think of the oracle, the friendly genie in the machine, and remember what it taught us. The journey to find shortcuts often teaches us more than the shortcut itself. Keep that curiosity and enjoy the wonders of theoretical computer science, where even imaginary machines have very real lessons to impart.